Let's talk about part 3 of measurement and resistance. In part 2, we have studied the substitution method used for measuring medium resistances, and we have studied all three cases. Okay, now we are moving on to the last case of the substitution method, and that is when your supply voltage varies. Okay, here we are having, suppose we are having two voltage sources. Okay, so voltage 1 is given by this particular formula and voltage 2 is given by this particular formula. The current, however, is same. Why? Because the value of resistances don't change. So no matter what, if you change the voltage, the value of resistance don't change, hence the current through those resistances will not change as well. Okay, so we are equating both of these equations, and this is our answer. This is our required formula for the unknown resistance. Okay, then we have our Wheatstone bridge. Here this is your basic Wheatstone bridge with this as our standard variable resistance. This is our unknown resistance, and we have known resistance as P, Q and S. Okay, we have a galvanometer with some internal resistance as Rg, and we have a current passing through this galvanometer, that is Ig. Under balance condition, the voltage across D and B terminals are 0. Okay, and the current Ig passing through this galvanometer will also be 0 under balanced condition. Now this is a Thevenin equivalent circuit of this particular bridge. Okay, here we are trying to find out the VTH, which is given by this particular formula, and then we have RTH given by this formula. Now Ig is given by this formula here, but under balanced condition, you know that Ig equals to 0, which is equal to this value. Okay, now Ig here doesn't depend on Rg or Rs. Okay, here this current which is passing through the galvanometer doesn't depend on the standard resistance this and the internal resistance of the galvanometer. Okay, then we have VDB equals to 0 under balance condition, as I have said earlier, that the voltage across these two terminals will be 0. Then we have, this is the given formula at balance condition. Okay, if you want to find out the unknown resistance at balance condition, then this is your formula. Then we have certain definitions to be kept in mind. The first thing is current sensitivity. Okay, which is actually the ratio of the deflection in galvanometer to that of current. Okay, here you can see theta is the deflection and I is the current over here. Okay, Ig is the current through the galvanometer, and the unit is mm per microampere. For small current, if the theta is maximum, okay, if the deviation is maximum, then the device is said to be highly current sensitive. Okay, then we have voltage sensitivity, which is actually the ratio of galvanometer deflection to that of VTH. Okay, it is measured in mm per volts. Then we have bridge sensitivity given by this particular formula. Here it is the ratio of deflection to that of small change in resistance. Okay, this is your formula over here. It is measured in mm, and your bridge sensitivity is high when this particular condition is satisfied. P upon Q equals to R upon S equals to 1. Okay, so you have to keep these things in mind. Okay, with regards to Wheatstone bridge. Then we have limitations of Wheatstone bridge. Okay, it is not suitable for measuring low resistance because it cannot eliminate lead resistance, and neither it is suitable for measuring high resistance due to leakage current. Then we are having some applications of Wheatstone bridge, and that is for measuring pressure, force and flow, etc. Then locating cable fault. Okay, we have Untitled method, which uses the fund of Wheatstone bridge for locating fault in a cable. Okay, then we have Ohmmeter method. What we are doing here is we are having this particular circuit over here, and what we are doing is we are first we are trying to put this value as 0. As you can see, this is a variable resistance. We are turning this resistance into 0. This resistance here is not into action right now. Okay, then we have this current flowing through entire. Okay, we have this I1 value. If the value of I1 is 0, then your this unknown resistance is infinite. If the value of I1 comes out to be maximum, then your RT is 0. Okay, but if it is neither of the two cases, then what we are doing is we are first putting this into 0. Okay, this resistance is put to 0 value, and the current through this circuit is measured through this ampere meter. Now what we are doing is we are eliminating this particular resistance and we are shorting the terminal AB. Now what we are doing is we are adjusting this R2 resistance in such a way that the same deflection is shown in this ampere meter, the same reading comes out. Okay, only and only then you can know that this particular resistance is equal to this, because this resistance is already known. When you don't take out this resistance, the current withdrawn is by these two resistances. Okay, the series combination of these two resistances is drawing certain current from this. Okay, now what we are doing is, when we eliminate this, the current is due to the effect of these two resistances. Okay, and we are trying to equate it, and this is how we are finding out the unknown resistance. Okay, here R1 is the current limiting resistance and R2 is the zero adjustment resistance. Here you can see that V and A are in series. Okay, so this is your series ohm meter. In shunt ohm meter, we are having both of these in parallel. What we are doing here is, first we are supplying current over here. Okay, and we have certain values, like for example, if you are getting this value of I1 equals to minimum, then your RT is also 0. Okay, but if your I1 is maximum, then RT is also maximum. But if the value of RT is somewhere between 0 and maximum, then what we are going to do is, first we are trying to find out what the current is passing through. Okay, this this resistance over here and this resistance will draw some current. Okay, this is put to 0. Okay, first for we are putting R1 as 0, we are adjusting it to 0 value, then the current passing through this will be due to this resistance. Now what we are doing, we are eliminating this resistance and circuiting these terminals. Okay, then we are adjusting this resistance to such a level that it also shows the same deflection of I1. Okay, then this resistance will be equal to this unknown resistance. This is what we are doing. We are comparing an unknown resistance to that of a standard resistance, known resistance, which is variable in nature. You vary your known resistance so that it is equal and it creates the same effect as that of the unknown resistance. Okay, and then you are able to find the unknown resistance. This is what we are doing in shunt meter. But practically what we practically use the series ohm meter method in practical multimeters. Okay, in practical we are using this particular method. Okay, so this is all for part 3.